Hi everybody. This week we're going to be talking about truth table analysis, chapter 15 of your text. And let's just start off with a little bit of review. Let's talk about the replacement method a little bit. Let's say I give you the compound sentence, Alex will go to the movies, or it is not the case that Alex will go to the movies. We can translate that sentence A wedge tilde A. Now, let's say I wanted you to tell me whether that sentence is true or false. Let's see, you have one variable, A, and we're in a binary system of truth, so you know that there's only two possibilities. A could either be true or A could be false, and this would affect the ultimate outcome or the truth value of the compound as a whole. So let's assume that A is true. By practicing the replacement method, you would take the whole compound, replace the two A's that exist on either side of the wedge with a T. You'd negate the second A, or the second disjunct, which would become an F. Now you have a disjunction T or F, and according to the disjunction function, the compound as a whole would be true. Now let's say I told you that A is false. You would do and with the replacement method, you do something very similar. You would replace both A's in the compound with an F, negate the second disjunct to get a T, a true. You have a new disjunction, F wedge T, which, according to the disjunction function, is true. So now you have your two possibilities. The proposition A wedge tilde A is true in both cases, whether A is true or A is false. So that's a lot of work using the replacement method. As you know, that's what we did last week. But what we're going to learn this week is how to construct truth tables for compound sentences like A wedge tilde A, so we can discover when the proposition is true, when the proposition is false. Constructing a truth table is simply a more compact way to display the truth possibilities of any given TL formula. So let's go ahead and construct a truth table, and I'll talk to you about constructing a truth table for that particular proposition, A wedge tilde A. Now, first thing you should know is that truth tables are made of rows and columns. The rows are horizontal, and what you'll write on a row in a truth table are the truth assignments, which are basically the truth possibilities of the given variables of any TL formula. The columns represent a part of the compound as a whole. So for this particular sentence, you have A wedge tilde A. So that's 4 columns. You'll write 4 columns because each part of the sentence will get its own column, and those are vertical. So for this particular truth table, you have 4 columns and 2 rows. Always a good idea to have the proposition right on top of the truth value, so you can write the truth assignments directly under the variables, and the columns coincide with each part very neatly. There's an image for you here. The first thing you want to do is list the possibilities, okay? So since you only have one variable in this sentence, A, there's only 2 possibilities that we have to assess the compound as a whole according to. A could be true, or A could be false. So in row 1, you have basically what if A is true. And you have 2 trues, true in row 1, column 1, and a true in row 1, column 4. And then the other possibility is that A is false. So you would want to present that and write that in on the truth table. So you'd have a false, or an F, in row 2, column 1, and a false in row 2, column 4. So first thing you want to do is you want to list your possibilities, you want to fill in the truth table, and then the second thing you want to do is start assessing the truth relations that are within the compound according to the different operators, and definitely, obviously, according to the main operator will be your final step. So Initially though, you want to begin with the operators or the connectives that have the smallest scope. So what I'm going to show you right now is a slightly more complicated TL formula, and we're going to go over constructing that truth table together. Now the formula we're going to be looking at is, I'll read it out to you, parentheses A and B, in parentheses, wedge, tilde A. Okay, so this is a larger compound. You have two variables, A and B, okay? And you have three operators. So this is going to generate a much larger truth table, okay? But we're going to go over it step by step right now. All right, as we went over in the first example, step 1, list possibilities, true possibilities for A and B, okay? So we can consider it like this. Perhaps A is true and B is true. Perhaps A is true and B is false. Perhaps A is false and B is true. Perhaps A is false and B is false. So what you have is you have four possibilities, four possible truth combinations given the limitation of a binary truth system and two variables, all right? Because you have four possibilities, you know this truth table is going to have 4 rows. So that's a decent place to start. Now, when you're constructing the truth table, don't forget, every part of the formula gets its own column. So this particular formula has 6 parts. So this truth table is going to be 4 by 6, 4 rows by 6 columns. Step 2, fill in the possible truth assignments or truth values to the variable columns, all right? You have column 1, column 3, and column 6. Column 1 and column 6 are both A, and you would fill those out true, true, false, false. So from row 1 to row 4 in column 1, it would be true, true, false, false, and that's the same for column 6. B, which is column 3, slightly different. True, false, okay? So from row 1 to row 4 in column 3, true, false, true, false. Once you've done that, you can start calculating the truth values of the embedded sentences, okay, inside the larger compound, or the various components of the compound sentence you're trying to understand here, okay? As I said, you always want to go with the smallest scope first, okay? So the operator with the smallest scope, it's a toss-up, right? Is it the tilde? Is it the ampersand? In the event that you have operators with equal scope, it doesn't matter which one you assess first, okay? You wouldn't want to assess an operator that has a larger scope prior to assessing an operator with a smaller scope. But if they're equal, you can go ahead and assess whichever one first, as long as they're equal in reach, okay? I went ahead and calculated the tilde first. So that's calculating column 5. You want to calculate column 5 according to the negation function. Column 5 negates the truth value of column 6. That's how the negation function works. So if you look at column 6, it's true, true, false, false. The negation of column 6 as presented in column 5 would be false, false, true, true. Okay. Next, you would go to the ampersand and calculate column 2. That's the column with the ampersand, right? You're going to calculate column 2 according to the conjunction function that is between columns 1 and 3. So column 1 is the first conjunct of the conjunction. Column 3 is the second conjunct. Column 2 represents the truth value of the conjunction, which is a component sentence to the overall disjunction, all right? Now, if we look at the truth values in columns 1 and 3, sometimes they're the same, sometimes they oppose. In the very first row, A is true and B is true. we know that according to the conjunction function, if both conjuncts are true, the conjunction as a whole is true. So in row 1, column 2, you have a true, because you have a true conjunction. In rows 2, 3, and 4, you have false conjunctions, because in all 3 of those rows, the truth values in columns 1 and 3 mismatch. And we know that a conjunction is only true if both conjuncts are true. Okay. Finally, the final step is you want to calculate the final column. The final column is column 4. That is the wedge. Calculating the wedge according to the inclusive disjunction. In fact, all of the disjunctions that you calculate in this chapter will be according to the inclusive function, so just remember that. Okay? So you're going to be assessing the truth value of the disjunction, which is P or Q, the disjunction function, okay, according to the 2 disjuncts. The truth values of the 2 disjuncts are represented in columns 2 and in columns 5, all right? Column 2 gives you the truth value of the conjunction, which is the first disjunct. Column 5 gives you the truth value of the negation, which is the second disjunct, all right? So when we're going to calculate, we're going to compute the ultimate truth value of the disjunction and ultimately the possible truth values of this formula according to the truth values in column 1 and the truth values in, column 2 and the truth values in column 5. All right, so let's take a look at the truth values in column 2 and column 5 and see how they relate according to the disjunction function. In row 1, you have a T and you have an F, which is a true disjunction. In row 2, you have an F and you have an F, which is a false disjunction. In row 3, you have an F and you have a T, which is a true disjunction. And in row 4, you have a false and you have a T, which is a true disjunction. All right, so what have we learned about this formula? We've learned that this formula is only false in one of its possible truth combinations, one of its possible cases, okay? So what you're doing is you're gaining insight into the logical status of this formula, all right? So far we've gone over an example with 1 variable, we've gone over an example with 2 variables, and next we would go over an example with 3 variables, and what you would have there is you'd have 8 rows. Every time you have a formula with 3 variables, you have 8 rows, okay? No matter how many columns, you're obviously at least gonna have 3 columns, but, and the possible truth values would go as follow, right? Like let's say for a formula you had 3 variables, A, B, and C, and you would need to consider the list of possible truth assignments for 3 variables. Every time it'll be if A is true, B is true, C is true. If A is true, B is true, C is false. If A is true, B is false, C is true. If A is true, B is false, C is false. If A is false, B is false, C is true. If A is false, B is true, C is false. If A is false, B is false, C is true. If A is false, B is false, C is false. Every time, that's what it's going to be when you're working with 3 variables, 8 rows. All right, let's talk about a principle of propositional logic, which says every sentence is true, false, or contingent. Now, a statement is contingent if there are possible circumstances in which it would be true, and there are possible circumstances in which it would be false. Specifying whether a sentence is necessarily true, false, or contingent is specifying what we call the sentence's logical status. A logical status for any sentence is either true, false, or contingent. Now, we can test the logical status of any compound sentence with truth tables. A sentence that is true in all circumstances and false in none is called a tautology. The tautology test states that a formula in TL is a tautology if and only if the final column of the truth table is true. So let's take the statement, it's not the case that both Annette is 40 years old and that she is not 40 years old. Okay. Yeah. Dramatic pause. We would translate that into the formula tilde parentheses A and tilde A end parentheses. Now I've constructed the truth table for you, which you'll see here. And you'll see that the final column, column 1, is all T's. And so this is an example of a tautology. It passes the tautology test. This particular formula is true in every circumstance and false in none. Now, a contradiction is the opposite. It is a sentence that is false in every circumstance and true in none. We can perform the contradiction test, which claims a formula of TL is a contradiction if and only if the final column shows all F's. I have constructed a truth table of the formula A and tilde A to show you a contradiction test, as you'll see. And you see that in the final column, column 2, there are all F's. And so this proposition, this compound sentence, is a contradiction, meaning it is false in every possible circumstance and true in none. Now, the final possibility, the final logical status that we're talking about is a contingent statement. The contingency test says this: a formula of TL is contingent if and only if it shows at least one true and at least one false. So in some certain circumstances, the compound sentence may be true, and in other circumstances, the compound sentence might be false. And we can see this if the final column of the truth table has some true and some false. I've written out the example for you for the formula G wedge tilde S. You'll see that it is in the second column, column 2, that you have got some true and some false. And for that reason, the proposition G wedge tilde S is contingent. That's the logical status. Now, for the exercises this week, 15.1 and 15.2, you will be assessing the logical status of compound sentences using truth tables. For 15.1, you'll be assessing substituted instances, which is compounds made up of atomic variables. And just to let you know, just some new language, atomic refers to a simple sentence, a variable that represents a simple sentence in TL. And another term that's used more frequently in this chapter is connective. And a connective in TL is an operator in English, okay? So a main connective is a main operator. An atomic variable is simply a simple sentence represented by one letter, for example, right? Now in 15.1, you'll be dealing with various instances, okay? In 15.2, you'll be dealing with sentence forms, where the variables will be represented by P and Q. Okay. And finally, I thought I would go over number 16 with you. I've constructed the truth table for you, which you'll see. The reason why I chose 16 to go over with you is it's a much larger proposition. So I just wanted to show you, give you some evidence that by following the same procedure as we did with the smaller propositions in the beginning of the video, we can accomplish the same thing, which is simply completing a truth table. As long as you follow the procedure and make sure that you are accurately applying the truth functions, you should have no problems with accuracy in your truth table. So let's go over number 16. The compound sentence is a biconditional. The antecedent of the biconditional is in brackets, and it reads, if A, then, parentheses, B or C. The consequent of the biconditional is also in brackets, and it reads, if A, then B, or if A, then C. Okay, now although you have a number of component compound sentences in this larger compound, you still only have 3 atomic variables. So you're still only working with the possible truth values of A, B, and C. So you're going to write out those possible truth values, just like we did a little bit earlier in the middle of the video or so. And that's always going to be the first thing you do, is list out the possibilities. Second, you're going to write the possibilities in the truth table under the various instances of A, B, and C. A appears in column 1, column 7, and column 11, B in column 3, column 9, and C in column 5 and column 13. Okay, next you're going to ask yourself, what is the main connective? And also, which operators have the smallest scope? Now, the smallest operators and the smallest connectives in this compound sentence are the ones that exist inside the parentheses. So they're represented by column 4, column 8, and column 12. The second smallest are the operators that are inside the brackets, and they are represented by columns 2 and columns 10. And finally, the main connective is the triple bar, because the sentence is biconditional, and that is in column 6. Okay, so now that you have all this filled out and figured out, you can start calculating the possible truth values inside the truth table. So first, you want to calculate column 4, which is the disjunction, P or Q, using columns 3 and 5. Next, you want to calculate column 8, which is a conditional, using columns 7 and 9. Next, you want to calculate column 12, which is a conditional, using columns 11 and 13. Next, you want to calculate column 2, which is a conditional, using columns 1 and 4. Next, you want to calculate column 10, which is a disjunction, using columns 8 and 12. And finally, you want to calculate the biconditional, the triple bar, which uses columns 2 and columns 10. Now, you'll notice column 2 and column 10, which is what you calculated from the brackets, were calculated based on what was the result of the components within the parentheses, all right? So you just work from the smallest to the largest, okay? And you'll see in conclusion that this sentence is a tautology, because every instance in column 6 is true. All right, guys. That's about what I have for you this week. I did attach a blank copy of a truth table in the week 13 assignment folder for you to work from. And if you have any questions about this material, please feel free to message me, reach out, and I'll go over it with you. Have a great week.